Okay, so there was a problem, it seems, with the internet. Sometimes it happens. And so the last screen was not visible. And so I've taken a photograph as well, which I will be sending people. Or I have already sent people, I guess, or something. But yeah, that's, by the time you see this video, I have not yet sent it. By the time you see the video, I would have, hopefully. So what we ended with last time was examples of diagonalizable matrices. So we first of all defined diagonalizable, which is just that it has a basis of eigenvectors. Then we said that a matrix is diagonalizable if and only if it is of the form PDP inverse. Those kinds of matrices we have seen before in the previous class when we started the chapter on eigenvalues. Examples of some. So first of all, that already tells you that every diagonalizable matrix is of the form PDP inverse. So what do I mean by examples? Well, examples that cannot be deduced from such things from that result. First of all, if f is the real numbers and a is any square symmetric matrix, real of course, then a is diagonalizable. This is an important result called the spectral theorem, which we will see in due course. Right? And then there is a is lambda 10 lambda. This is an example of something called a Jordan block, and this is not diagonalizable. How do you prove something is not diagonalizable? It's hard to say that there exists no P and D. So the way we prove it is using that next result. That is why that result was there, that it's diagonalizable if and only if it has a basis of eigenvectors. So if you want to prove something is diagonalizable, just find the basis. That's the same as doing PDP inverse. If not, then you prove that there cannot exist one. And so why not? Well, first of all, look at the characteristic polynomial. This is x minus lambda squared. It's an upper triangular matrix. If A was diagonalizable, so the eigenvalues are lambda and lambda, right? So therefore, if A was diagonalizable, it would have a basis of eigenvectors for lambda and lambda, which means that A v1 equals lambda v1 and A v2 equals lambda v2. But we also know that the identity matrix times lambda acts on these basis vectors in exactly the same way. So A and the identity, lambda identity, are two matrices which act on the basis, this basis of eigenvectors in the same way. So by a homework or class problem or something, A must be equal to lambda times identity, but of course it isn't. This off-diagonal entry is non-zero. That's a contradiction. And what is it a contradiction to? It's a contradiction to this assumption that A was diagonalizable. Therefore, A isn't. Okay. So that was where we stopped. And as I said, I would remind you of this today. So let's start. So today we are going to start with the AMGM inequality. It is not the arithmetic mean geometric mean inequality. It is the algebraic multiplicity geometric multiplicity inequality in linear algebra. So recall again, given a matrix, a square matrix, a scalar, the algebraic multiplicity of lambda is a number of roots of this characteristic polynomial that are equal to lambda. So in this case, the algebraic multiplicity is 2. So in general, it is whatever it is. And the geometric multiplicity is the dimension of the eigenspace, the lambda eigenspace. Okay, so now the proposition, now the AMGM inequality. Suppose V is any finite dimensional vector space and T is a linear transformation. I could have done the same thing for T, and I will leave it to you guys to check that it is well defined and it's all the same thing. Right? Then either lambda is not an eigenvalue of T or of A or whatever, and then the AM and the GM are both 0. That is almost obvious from the definitions as we use right now. Or lambda is an eigenvalue, and then both AM and GM are strictly positive, so bigger equals 1, but also AM is bigger than or equal to GM. And that is what we have to prove. Okay, so now let's start. So let's start the proof. Okay, so maybe for a change, I will start at the beginning of the class. So if lambda is not an eigenvalue of T, then clearly AM is 0 because there are no roots. Eigenvalues are the roots of the characteristic polynomial. There are no roots, so AM is 0. But also, something is an eigenvalue if and only if this kernel is non-zero. So if that is not an eigenvalue, the kernel is 0. Then AM equals GM equals 0. Follows immediately from last class. Or this different class. Okay, so that is part one. Okay. So now let us suppose lambda is an eigenvalue. So that first of all, the AM and the GM are both, sorry, it's not A anymore, it is T. First of all, they are strictly positive. Now what do you do? Now what we do is the following. So because AM is AM, okay, I think I should give it a name. Sorry, let's give AM a name. Sorry, GM a name. Sorry. So V1, V2, VR. Yeah. So R is the name. So say GM. I keep writing down A, but T. So if the geometric multiplicity is equal to R, let's call it some name, then that means there is a basis. Sorry, that means the vector space which is the eigenspace, has an R-dimensional basis. Well, has dimension R. Therefore, it has a basis of psi R. So, not thinking clearly. Fix a basis. Fix an ordered basis, in fact, why not? V1, V2, VR of V lambda, which is the kernel. Okay? Great, so fix this ordered basis. Now let's extend it to a basis of the entire vector space V. Let's say the V has dimension n. And let's put that basis before this basis and call that a big ordered basis. Extend to an ordered basis. Extend this, if you want, to an ordered basis. And now I'll write this down. B equals, let's order basis of V. B equals, let's call them W1, W2, Wn minus R. And then V1, V2, Vr. Okay, so this is an order basis of V. And let us write down the matrix. And write down the matrix of T with respect to B comma V. Okay, so I'm going to write this down. Now, how do we write this down? So this is W and then V. So first of all, okay, so if you look at T, V, J, then this is literally lambda J, lambda Vj. Lambda is the fixed eigenvalue and the Vj's are eigenbasis, or basis of this space. Right? For all 1 less equals J less equals R. And now what about TWI? TWI is, well, I don't know what it is. So it's some combination of WIs plus some combination of the Vj's. So let's write this down. Let us say Cij Wj. J goes from 1 to n minus R plus D. No, I think I want to say Dij Wj plus Cij. I normally write Cj Vj, right? So Cij Vj. This time J goes from 1 to R. For all 1 less equals I less equals n minus R. Because these are all the matrices. This is how the linear transformation acts. I'm writing it down in terms of the basis B, the ordered basis, and therefore I can write this matrix down. Okay, so ordered basis therefore implies that TBB is how much? So the first rows correspond to the W's and then the first columns. So it's basically something like this. It is something like Cij or maybe Cji, I don't know, Dij, sorry. Dij or Dji, whatever. And then Cij or Cji, again something. And then you see here, there are no W terms. I just get a big 0. And here, what are they? So in the jth row and the jth column, you get a lambda, and everywhere else you get a 0. So you just get non-zero entries along the j comma j entries. So you get a diagonal matrix. And what are the entries of the diagonal matrix? They're exactly lambda. All of them are lambda. So I can take the lambda outside and I get a diagonal matrix with ones on the diagonal. There is a name for such a matrix. It's called the identity matrix. So I take lambda outside, I get the identity matrix of size r. Okay. And now I want to take the characteristic polynomial, right? I want to talk about I know the GM is R. I want to talk about the algebraic multiplicity. So I need to take the characteristic polynomial. So Pt of x, I can therefore say it is determinant of with respect to this basis, xid minus pdv. Okay. And now again, what is this? This is equal to determinant xid minus dij and minus cij 0 and then x minus lambda identity. And you see, this is a block upper triangular matrix. And we have proved the formula for block upper triangular matrices. Of course, this is over the ring with an x in it. So it's like over fx. But I could work in the field f at joint x. So block upper triangular semicolon work in f rational functions. This is a field. This is a field. Work in the field f bracket x, f parentheses x. This is the set of all rational functions, set of all ratios of polynomials, as we said. And so because of that now, this determinant is it's a block of a triangular, so I can multiply. So it's the determinant of xid minus the dij. But this is some polynomial. I don't care what it is. It's the characteristic polynomial of the D matrix. Right? Let's say the just call it B here. Times, well, this is, what the determinant of a diagonal or a triangular matrix is. It's the product of the diagonal entries. So you have a polynomial where already there are lambda, r many roots equal to lambda, and there might be some others. I don't know. Maybe the lambda is a root of this also. In any case, certainly since r is already here, at least r copies divide the characteristic polynomial, and therefore the an is really equal. So we are done. Okay, great. So that is that. What is next? So I should point out now here that not every where is the I should point out that not every matrix has eigenvalues. Okay, so as I said, sometimes you may not have eigenvalues, right? So, but in fact, so far I think I've given you examples of matrices where there are always eigenvalues. So now let me give you an example of a matrix where there isn't one. Consider the rotational matrices basically. So, remark. Not every A belonging to f to the n cross n has eigenvalues. For example, let's say the field is the real numbers. A equals 0, -1, 1, 0. It's a rotation matrix. Cosine, negative sine, sine, cosine. Okay, and so this is characteristic polynomial. You can check it is what? It is x 1 minus 1x, the determinant of that, which is x squared plus 1. And of course, x squared plus 1 does not have any roots in this field. Of course, it has roots in the complex numbers, I and minus I, but not over R. So, A does not have real eigenvalues. Of course, it has complex eigenvalues. And the difference stems from the fact that complex, so real numbers, or there are over real numbers, there are polynomials with real coefficients which do not have any real roots. Basically, this polynomial. But over complex numbers, this is not the case. For every complex polynomial, it has to have a complex root. Every real polynomial also has to have a complex root. So, and that is what happens. Actually, the good news is that happens for every single field, whether finite or infinite, whether characteristic is 2 or 3 or a positive number or 0. No matter what field you start with, you can always embed it inside a bigger field such that every polynomial in the bigger field, over the bigger field, and therefore over the smaller field, factors completely into a product of roots, linear factors. So every polynomial has a root, so you can divide by the x minus lambda, the factor theorem, you come to a polynomial of smaller dimension, keep going. These polynomials are, these fields which have this property are called algebraically closed fields. And so let me just say that analogously. Every field right, can be extended or sits inside, if you will. Okay, which call its algebraic closure. Yeah. So algebraic closure means it's the smallest algebraically closed field. Anyway, it's the smallest possible field with the following property. Which has the property that every polynomial over f bar has a root. F bar of x, in fact, maybe I should just say P belonging to has a root in f bar. And so for the Algebra 1 students, you will either see this at the end of your course or in Algebra 2. Or equivalently, Px factors as a root of, is a product of x minus lambda times some c. For scalars, c and lambda I in f bar. Okay, so every polynomial basically factors like this, or equivalently, it has just a root. And therefore, over f bar, if you take any matrix A over f bar, then of course, all the eigenvalues exist. Now, if A is a matrix with entries in an algebraically closed field, then all its eigenvalues exist. Then PA of x also has such a property, and therefore, yeah. then all eigenvalues. Then let me say applying this fact to EA of X, what we get is that all eigenvalues so basically we are saying take any algebraically closed field and then take any matrix, square matrix with entries in that field, and all the eigenvalues lie. Again, that's going to motivate my next result. So in my next result, what I'm going to say is, suppose I have a matrix, all of whose eigenvalues lie in the field. So remember, we started today's class with diagonalizability, and then we went on to AMGM, but over here there was no diagonalizable matrix. It was just for every matrix, AM is bigger equals 0. But now, as I think I told you last time, now we will talk about the arithmetic means, the algebraic multiplicity given in AMGM equality as the if and only if for diagonalizability. And for that, I need the fact that my eigenvalues are first of all, this only works for matrices whose eigenvalues lie in the field. So, for example, if the field is algebraically closed. Okay. But it need not be that way. For example, a diagonal matrix over any field is diagonalizable, and of course, its eigenvalues lie in the field. So you don't need the eigenvalues to. No, the eigenvalues are the roots of the characteristic polynomial. But if the matrix is already diagonalizable, or even better, diagonal, then I don't need to use characteristic polynomial. The roots are already elements of the field. So either way, I need to be given that my matrix eigenvalues are in the field. And an example of that is if my field is algebraically closed. Okay, let us now therefore with that write our next result. Is this a corollary or what is this? I think I should call it a proposition. It doesn't make sense to call it a corollary. It's too big a proof. I won't say in linear algebra this time, okay? Okay, so suppose, should I state this one for, I'll state this one for matrices because there's some algebraic closure stuff. So say A belongs to F to the n cross n has all eigenvalues in F. Okay, so this is one special example of this is if the field is algebraically closed. Okay, so suppose I have such a matrix, then A is diagonalizable if and only if for all lambda in F, okay, or I can, so okay, let me just say this. Am of lambda equals Gm of lambda. If and only if this happens. But now we saw last in the previous result that whenever lambda is not an eigenvalue, this is already true because both are equal to 0. So I want to tell you that so I don't need to worry about the non-eigenvalues. For them, both sides are 0. I just need to worry about the eigenvalues. And that's what I said for all lambda e values. Because the advantage of this is that the field may be infinite, but this is just a finite set of conditions. You just need to verify finitely many equalities of numbers. Because eigenvalues are finite. Even if the field is uncountable, the dimension is finite. So the number of eigenvalues is finite. Okay, great. So that is the theorem. how does one prove it? Which side do I want to do first? Okay. So first of all, let's just start writing down some preliminaries and then set some notation. Okay, so first of all, lambda not equals eigenvalue implies that. So I'll just say that. Eigenvalue implies am equals gm equals 0. So that is fine. So that is true regardless of whether A is diagonalizable. But all I'm saying is I can just forget about this because of this reason. Okay, so first of all, that is one point. Another point is we already know. So okay. So we already know that PA, like we are given that PA of X. Since A has all the eigenvalues in F, so we already know or given that PA of X splits into linear factors. Exactly like this. Because we know the roots exist in the field. Well, I'll even tell you what the factors are. They are precisely X minus lambdas for X minus lambda equals E value. Now, of course, there can be repetitions, right? The whole point of AM and GM is that repeating eigenvalues can occur. So let us write down the distinct eigenvalues and write down how many times each of them occurs. And I have notation for that, lambda 1, lambda 2. So let lambda 1, lambda 2, lambda k denote the distinct eigenvalues. With multiplicity, meaning algebraic multiplicity, M1, M2, Mk respectively. Okay, so therefore that means M1 plus M2 plus Mk equals N. Okay, great. So now let's continue. Fine. So what do I want to do? Okay, so I think now am I ready to now do if and only if? Okay, well I'll just write this down once more. So if this is true, then that means that I can say PA of X. I mean, this is just obvious from the notation, but is a product X minus lambda I to the N I goes from 1 to K. And that is literally the characteristic polynomial given these algebraic multiplicities. Okay, now I think we can prove it and only. Which way are we doing first? Okay, this is okay. So diagonalize. Suppose A is diagonalized. So this is if, and this is only if, and this is if. Let's prove the only if. Okay, so since A is diagonalizable, and let's see, what am I saying here now? There is a basis of eigenvectors. Right? So these are the eigenvalues, and for these eigenvalues, there's a basis of eigenvectors from above, from the previous result. A is diagonalizable. There exists a basis of eigenvector. And I'll just call them V ij. 1 less equals I less equals k, and 1 less equals, so for every I have lambda I eigenvectors with A times Bij, of course, equals lambda I times Bij for all I and j. Now what do you do? Well, that means that I have at least I have Vi1, Vi, Mi. These are how many? These are linearly independent vectors, sorry, I'm just too many alarms, are linearly independent vectors in V, so in lambda I. So V, of course, is F to the n here. In the eigenspace, because they form a basis. So that means in particular they're linearly independent and all of them lie in here. So therefore you just get this. But what does this mean? This means that the dimension of V lambda I, sorry, let's just write it down in one line and finish. The dimension, okay, let's start with the geometric models. Okay. So Gm A of lambda I, which is the dimension of V lambda I. Well, these form a linearly independent set, so you can extend that to a basis. So the dimension of the size of a basis is bigger than the size of the linearly independent set. But the linearly independent set Mi has size equal to the algebraic multiplicity of lambda I. And we know that the algebraic multiplicity, we now use the AMGM inequality. So basically you got the reverse inequality and now you use the usual one to prove that they're equal. And this is true for all I. So we are done. Okay, great. So that is that. Conversely, now we want to say that suppose I know AM equals GM. Let's prove that A has a basis of eigenvectors, or let's prove that A is diagonalizable. Now it's so okay. I think I proved this last time. I did. That if you look at the eigenspaces and you look at the sum of those eigenspaces, then that sum is direct. So in particular, what does it mean to say the sum is direct? It means that the basis, the union of the basis of each of those guys, of each of the eigenspaces, is the basis of the whole space. The union. Okay, that's what we will use. So how do I want to say this? Gm equals am. So let's start with these linearly independent eigenvectors. I'm not writing down Gm, A, lambda I. So start with bases V I1, V IMI of V lambda I. V, of course, is F to the n again for each I. Okay, so because we know that this is now a basis, it's not just linearly independent, we know the dimension is equal. So remember, I denoted the dimension before I started the if only. So these MIs are already known to me. They're already set as notation. Okay, so we have this here. Now what do I do? Well, now we literally use this thing. So now we use the fact that the sum is the direct sum by previous result. The sum V lambda I is direct. So what is this dimension? Hence has dimension equal to summation dim V lambda I equals summation Mi, but that is the full dimension n. The whole point was the characteristic polynomial has degree n is f to the n, yeah, and therefore all the mi's, these are the distinct eigenvalues. These are how many times each of them occurs. Because all the eigenvalues lie in the field, whether the field is ultimately closed or not, all the eigenvalues lie there. So therefore, this summation is exactly equal to n. Let's look at this equation. Both sides have degree n. So yeah. But what does that mean? Remember that the bases are linearly independent anyway. So the union of all these elements form a basis of the vector space. The co-product of the bases forms the basis of the coproduct, basically. Yes, and hence the same thing is this whole thing. Bij forms a basis of f to the n. But also remember, these are in the eigenspace, so they all consist of eigenvectors. Consisting of eigenvectors. And so I'm done. A matrix is diagonalizable if it has a basis consisting of eigenvectors. Okay, so that is that. I think I need some water now. Well, I'll just add a homework problem and then I'll take a small sip of water. So in particular, so let me then show you another example. One more example. So we said that of course this matrix is not diagonalizable because it's the upper triangular and the entries are the same and we have a problem. But what if I do something like this? Lambda 1, lambda 2, lambda n and star. And I know all the lambdas are distinct. Now clearly this is not a diagonal matrix because there can be non-zero entries above it. But if all the lambdas are distinct, then you can check that AM equals GM always because well, both are actually equal to 1. And so it is diagonalizable. So in particular, basically, this is just a special case of the fact that if you have any matrix whose eigenvalues are pairwise distinct, for a triangular matrix, it's easy to tell what the eigenvalues are. But you don't need the matrix to be triangular. You just need it to be having distinct eigenvalues. No repeated roots in the characteristic polynomial. So let us write this down. Then I will take a break. More generally, work. Say A or T, the usual linear transformation as pairwise distinct. Sorry, actually let's just forget that here. So A in f to the n cross n has n distinct eigenvalues. In f, of course, then A is diagonalizable. Of course, the converse is clearly not true. For example, if A is diagonalizable, it need not have distinct eigenvalues. For example, the identity matrix. It has all the same eigenvalues. But of course, it is diagonal and hence diagonalizable. So the converse is not true, but certainly if A has distinct eigenvalues, that is a very easy way to check, to know that it is diagonalizable. So even if it looks very, very non-diagonal, like a completely upper triangular matrix, but as long as the eigenvalues are distinct, you can find some basis, an eigenbasis. Okay, now I will take a break. Okay. So now we come to something called the Cayley-Hamilton theorem. This is going to be very interesting. Okay, I'll do the Cayley-Hamilton and I will stop. This deserves a separate. So this is all about the basics of eigenvalues. You can think of the following as the next section. in the eigenvalue chapter, there are at least one more section, the minimal polynomial. So today we will do Cayley-Hamilton, and next time we will look at the minimal polynomial. So let's start. This is a very nice theorem. It's a very remarkable theorem. So the idea is the following: take a matrix and look at all the polynomials that kill the matrix. So the first question, so clearly P of x equals 0. Replace every entry by 0. That kills the matrix. Sure. Great. But can you do better? Are there non-zero polynomials that kill the matrix? If there is a non-zero polynomial, look at the top degree coefficient, whatever the highest degree coefficient is, divide by that. So you will get a monic polynomial. Monic just means the top degree coefficient is 1. So let me just mention that. A polynomial is monic. Of course, it has to be non-zero in order to have a top degree coefficient. It's monic. If it's leading coefficient or highest degree term or coefficient, okay, so basically, as long as there is a non-zero polynomial that kills the matrix A, a square matrix over a field, you can divide by the top degree term and get monic polynomial. Fine. So do there exist such polynomials? The question is that. The answer is yes, they do. They exist for every single square matrix over every single field. And the polynomial itself is extremely well known because we have been seeing this polynomial infinitely many times over the last chapter. So let us see some examples. The question is really that, as I said, given A belongs to F to the n cross n, does there exist a monic polynomial such that let's call it P belonging to Fx such that P of A is 0. Okay, how do you prove this? How do you check this? Let's do some examples. So example is that P of A, let's say, let's do lots of examples. Example 1, A equals, let's say, identity matrix. So it's just ones and zeros. Now, if you look at x minus 1, then what do you get when you apply this to A? You get A minus 1. But what is 1 in this polynomial sense? It is the identity matrix. This indeed kills. And similarly, I'll call this part A, and similarly part B. If A is lambda times identity, then you can just get P of x equals x minus lambda, obviously. That works. Okay, now let's do a slightly different one. Let's do, these are of course diagonal and diagonalizable matrices. Maybe I will do one which is not diagonalizable. I'll do that one, sure. A equals lambda, lambda, 1, 0. Now if you take x minus lambda, then you don't get the 0 matrix. You get 0, 1, 0, 0. But the point is, if you square this matrix, you get 0. So if you take x minus lambda square, then you get 0. So great. So you get so great. And we are finding all these non-zero monic polynomials. The top degree term is 1 times x, 1 times x, 1 times x squared. Let's look at the next one, which is a diagonal matrix with distinct eigenvalues like this. Okay, so and this is going to be fun now. Let's see. This was 2. Actually, I don't even need distinct eigenvalues, right? So let me look at this matrix. Well, let's say this thing. Lambda I distinct. Now can we find the polynomial? So now, of course, x minus lambda or x minus lambda square will not work. There are all these different eigenvalues. But if you look at x minus lambda I, let's look at x minus lambda 1. So when you do this minus lambda 1 times identity, the first entry becomes 0. If you do this minus lambda 2 times identity, the second entry becomes 0. And so on. Right? So if I take x minus lambda I, the ith entry is 0, I still get a diagonal matrix where you have lambda 1 minus lambda I, lambda 2 minus lambda I, dot dot dot, lambda I minus lambda I, which is 0, and then the remaining things minus lambda I. So if I have these n different matrices which are lambda j minus lambda I, where you run across all j and fix a lambda I. And each of these matrices has a 0 in a different position. So if I multiply all these diagonal matrices out, you know that the product of diagonal matrices is just the product entry-wise, diagonal, diagonal, diagonal. So in every diagonal position, one of these matrices has a 0, so the product is 0. So the entire diagonal becomes 0 and I'm done. Right? So check, I'll just say check. X minus lambda I applied to A as I entry 0 is diagonal with I entry 0. Oh, sorry. Is diagonal, sorry. So this is obvious, I mean. So Px equals product. So check that this works. Check that Px equals I goes from 1 to n, x minus lambda I works. This is a monic polynomial which will kill the matrix A. And now we come to example 4. Suppose indeed my A was like this, except I had the star here. I had non-zero entries here. Lambda I are distinct, and A equals this matrix. Certainly it is diagonalizable. But what can you say about a polynomial that kills it? Claim the product of x minus lambda I still kills it. I understand that if I do this polynomial and I evaluate, this polynomial and evaluate P of A, the diagonal entries will be 0 because that is exactly like this. But why are the off diagonal entries also 0? Are they really 0? And the answer is yes, they are. And why is called the Cayley-Hamilton theorem. Claim P of A is equal to 0, even above the diagonal. The diagonal is clearly 0 by the previous example. Okay, and that is the Cayley-Hamilton theorem. So why? And the answer is it is not just true for upper triangular matrices or lower triangular matrices. It is true for every matrix over every field. In fact, over something more general than a field called a ring. So I'll write this down and then so see. What about Okay, so let's write down the theorem. Oops. Let's write down the theorem. Uh, and by the way, what are these polynomials? If you look at the polynomials here, this one is different. These two are different, but this polynomial x minus lambda square is the characteristic polynomial. The product x minus lambda is the characteristic polynomial and also of this. And that is the Cayley-Hamilton theorem. As I said, there is a monic polynomial which kills every matrix, and you have seen that polynomial so many times because it is simply the characteristic polynomial. So, given a field, so for all fields f, integers n bigger than equal to 1, and matrices A in f to the n cross n, so for all fields, all sizes, and all matrices, P A of A is the zero matrix. That is the Cayley-Hamilton theorem. Okay, great. Okay, so I'm going to prove it with quotes, with a caveat, namely that I'm going to assume that the proof that, so we will assume that determinants actually exist not just over fields but over arbitrary rings. So rings are structures like groups and fields and vector spaces which are closer to addition, subtraction, multiplication, but not necessarily division. So for example, the set of matrices forms a ring, but not all matrices are invertible, so you can't divide. Okay, so that. Okay, so let's just finish this and then I will stop. So the proof of Cayley-Hamilton. So today is a shorter class again. So I think 2 classes previously I took a very long class, like I went 15 minutes over time. So I did something less, or maybe 3 classes previously. Anyway, so I did something less the last since then, and today also is a slightly shorter class. It makes sense to stop at the proof of Cayley-Hamilton rather than start minimal polynomial. Okay, so Cayley-Hamilton proof. So the proof is first of all by induction. On n greater equals 1. The base case of n equals 1 is easy. The base case of n equals 2, you can also even check by hand. It's just obvious. Because in n equals 1, it's a diagonal matrix. And for diagonal matrices, we know that it works. Okay. Okay. N equals 2 also can be checked by hand. Okay. So now induction step. Cayley-Hamilton, right? Is there induction step here? No, I don't think there is an induction. I don't know what in the world I'm writing. I don't see any induction of any kind. Sorry. It's completely false. I don't need to do any of this. Sorry. What I do need to do is to assume that determinants exist for whatever arbitrary rings. Okay. So let's just do this. So okay. We are going to work over. So let's just say this. So we will this proof assumes. So this proof is again taken from Hoffman and Kunz, the textbook that I mentioned. There are several proofs mentioned there. This is the shortest and sort of the most conceptually beautiful, But it does require you to work over an arbitrary, over a ring that is not a field, and that may not even lie inside a field. That is the problem, right? So, nevertheless, whatever it is, so this proof from Hoffman and Kunz assumes that for all commutative rings, so commutative rings with the one element, the multiplicative identity, a determinant function exists on R to the n cross n. And is unique and multiplicative. Okay, so I will not even need uniqueness. Well, no, let's say it's unique. Unique is good. So at least every matrix has a unique determinant. Okay, great. So now what do I do? So, so as I said, you can assume this because you can sort of start developing the whole theory and so on. Okay, but I won't actually do the whole theory of determinants. But we will actually assume this for just for this proof. So in that sense, you can maybe hand wave and say it's a proof. But fine, so be it. Okay, so now I write down the. I just literally write down what this is. So first of all, so now with this we start. Write A times E I or EJ. I want to say EI. So what is A times EI? It is the ith column of A, and it is ith column of A. Remember, column, not row. Normally you put I for rows, but I'm going to put I here. And so it is, instead of AIJs, the column entries are AJI now. As J runs across the rows, and this is what it is. Okay. But now on the other hand, this is the same as saying it is delta Ji A EJ. Also J going from 1 to n, where delta Ji is called the Kronecker delta. So I should write it somewhere maybe. Delta Ji Kronecker delta. Kronecker was a mathematician. This is 1 if j equals I and 0 if j not equals I. So literally the only term that matters is when j equal to I, you get 1 times A times EI because j equals I. Okay, great. So this is what it is. So now you get this equal to this. Both sides have EJ's summation. So that I take summation delta Ji A minus A Ji identity times EJ equal to 0 for all I. This should be summation over J obviously minus J. Okay, so I have a system of equations. And where the question is really, where are these system of equations? This is like a linear system of equations, but where are they landing up? And that is the tricky part. So let's call this maybe star, first of all. This holds in this system. So this system can be written as using the matrix, this matrix, M belongs to R to the n cross n, M I J entry is, I guess, this one, delta Ji minus and I need to tell you what is R. So each of these matrices has to sit inside R. Well, R is therefore the following form. Take the set of all. So where does A lie? A is a matrix in F to the n cross n. So R is going to be a subset, a subring of F to the n cross n, and it is going to be the subring, any subring, which includes A and identity. But I could even take R to be F to the n cross n. I don't know why Hoffman and Kunz want it to be the smallest such ring and this and that. Who cares? Yeah, it doesn't matter. I can say that R is F to the n cross n. Or, so to be strictly precise, R is any subring containing exactly the matrices we need to define this matrix M, A and identity. But I could just take R to be F to the n cross n. So I don't know why Hoffman and Kunz don't do that. Why do all this complication of subrings? Okay, great. So now, as I said, determinant exists, it's unique, it's multiplicative. So now, the star says, if you look at the M matrix, and you look at this is M or is it M transpose? I'm just saying star is M. Each entry acts on a vector in F to the n. This is F to the n square times 1. Ej, so E1, E2, En. So this gives you actually 0, 0, 0. This gives you 0 in F to the n, 0 in F to the n, 0 in F to the n. That's what the system is saying, that you're always getting 0. The only question is, what is the thing here? So if you have A11, E1 plus A12, E2. But this is I is being summed up. So I think this is M transpose probably. That's fine. M transpose is fine. So let's look at this system, right? So this system, it's just a system of equations which I'm writing this way. And now I can multiply by the adjugate of M transpose on the right hand side, on the both sides, pre-multiply. These are just again applying some linear transformations to this business. So I can just multiply them, pre-multiply both sides. Right, so I'm not multiplying really by a matrix. I'm just saying by multiplying on both sides, I'm just applying some linear transformations using A and identity to both sides, like A power n minus 1 plus Aij A power n minus 2, things like that. Because everything is 0, no matter what linear transformations I apply and how I regroup and take linear combinations, 0 stays 0. So no matter what linear combinations on this side I apply, I will still get 0. And that's what happens here. If you multiply any matrix in R to the n cross n on this side, 0 is 0, so that doesn't change. Re-multiplying both sides by the adjugate, I think we saw this last time, or maybe 2 classes ago. M transpose, what do we get? And this is where now the right hand side is 0, because adjugate of M transpose is 0. So 0, 0, 0. And that is the same as the original vector times the adjugate of M transpose. On the left hand side, what you get is the interesting thing. Because you get, first of all, you have E1, E2, En. You have M transpose. And then you have the adjugate of M transpose. But what is the adjugate of any matrix times itself whenever the determinant function exists and is unique and is multiplicative? This is what was one of your homework problems or in class. This is exactly the determinant of M transpose times the identity matrix. Of course, times whatever. And this is equal to what? This is equal to the determinant of M transpose is the same as determinant of N. No, let's keep it that way. Fine. Let's keep determinant of M transpose. Great. And so now, so what do we have? We have that this transformation, the determinant of M transpose is what? Where does it lie? This lies in R. Right? If you have any determinant function, it goes from R to the N cross N to R. So therefore, this whatever this quantity is, it is an element of F to the N cross N. It is a matrix. Right? The point is everything in I know how you need it. You need it because I want the ring to be commutative. So I need a commutative ring containing this thing, and this is why they define this. Okay. The word commutative here is important. Very good. Now I understand. So this is why they say, right, that if you want to really learn or understand a subject, you should teach it. So this is where you need the assumption. You need the ring to be commutative, otherwise how is the determinant defined? We don't know that. When R equals, so I just look at all the polynomials in A. That's a ring, right? So P of A, P X belongs to Fx. The RR is a commutative subring. Now, because it's commutative, of course, this works. This determinant exists, and it is an element of the same ring. In particular, of course, this is a matrix because remember, R was contained in F to the N cross. Okay, and now you so what you see therefore is this matrix. So let's call this. So let's give that matrix a name. I'll call it M little m. So M is det of M transpose. I'll just say is a matrix in F to the N cross N such that this equation holds. What is this? It's identity here and M here. So it's literally this is just M E1 E2 En. And so you get that M E1 E2 En is equal to 0 0 0. But what is this? This is literally Me1 Me2 Men. Okay. So I get that M is a matrix such that MEI equals 0 for all I. Which matrix in F to the N cross N satisfies that acting on the basis of 0? Well, you know that the 0 matrix times EI is also equal to 0 for all I. And if two matrices act the same way on the basis, then they're equal. So what we get therefore finally is that the determinant of this big bold cursive M transpose is a matrix in F to the N cross N, which must be the identically 0 matrix. Oops, no, this is why I don't want to delete this. If M is equal to that, then what is M transpose? It is literally delta ij A. I'll write this down nevertheless. Minus Aij, identity. I'll just put, why don't I even put the determinant here? What is this? This is so delta ij, so it's literally A only on the diagonals. Now I can erase this. I wrote this down. Okay. So A minus A11 times identity, I don't write that, minus A12 minus A1n minus A21, A minus A22, minus A2n, dot, minus AN1, minus AN2, A minus ANN. So I is this matrix, of course, where the scalars mean identity matrix, and I can still take the determinant because it is over a unitive commutative ring. But this determinant should look very familiar to you. If instead of A I had put in X, what would I get? I would get everything times identity matrix. Of course, all this thing X minus A11 times identity, this times identity. But it's the same identity matrix. It doesn't matter about it. So if I put X's here, I would exactly get X times identity minus capital A. Take the determinant, that's a scalar, and take that times the identity matrix, that is this determinant. So basically, it is exactly the characteristic polynomial of X applied to the identity times the identity matrix, where you apply instead of X, you put in X equals A. And that is why this is exactly PA of A. And so what we get is PA of A is the determinant of M transpose, which is an element of R, as I said, which is an F to the N cross N, and that element is equal to the zero matrix. So, module of believing that determinants exist over any commutative ring, this is the Cayley-Hamilton theorem. It's a very clever proof. All we did was we wrote down this very cleverly to say A Ej equals summation to be like the delta Ji times A. Delta Ji times A times Ej, that way. And then we wrote that the system of equations as a matrix equation like this, with the entries of the matrix coming from a commutative ring of matrices themselves, multiply by the adjugate, and you just get the determinant as identity. But the determinant itself is a matrix, so you put the matrix times identity here, E1 equal EM. So you get each MEI equals 0. The only such matrix M has to be the zero matrix, and so M is 0. And now just write out what is the M, which is the determinant of this thing, and it's just the K. So if you see the amount of mathematics we did, it was mostly to switch around notation, to define the script M, to set up this equation system in a different way. And the only math we actually did was to derive the system of equation by saying A Ej equals Aij Ej or whatever, summation, and then to pre-multiply by a matrix and use the determinant, the property of the attribute. Those are the two mathematical steps we did. Everything else is just interpreting it in the correct way. But that's why it's the most conceptually simple proof of the Cayley-Hamilton theorem, if you will. It is also the most non-trivial or most crazy, or how do you derive it? How do you think about this? But anyway, that is what it is. Okay, so that's it for today. Next time, as I said, we will start with the minimal polynomial. Let me just allow you guys to see this. Okay, so we will start with the minimal polynomial next time.